This part is a simple demo of how to use the visualization feature of semaphores in ThreadMentor. It is a short and simple one, but I hope you can learn something from ThreadMentor's semaphore capability so that you could write your program for in a rather easy way. The example we're going to talk about is the four-chair philosophers problem. So here I have already compiled the four-chair dining philosophers version with visualization and run it. So far, as you see from the history window, the main program runs for a while and is created here. As we discussed several times in an earlier demo, the two most useful window, the two probably you'll use very frequently, are the history window or history graph window and the thread hierarchy window. So let's run this program for a few steps. Now, here, as you can see, the main program created philosopher 0 and philosopher 1. Then philosopher 2 are created. The main program then joins with the first created thread, which is, of course, philosopher 0. As a result of this joining, the main program has a blue bar. Now, if we run enough number of steps, now you see green bars. They mean running. This blue bar means joining. These red bars indicates threads are blocked due to whatever reason related to a synchronization primitive. Recall that in this four-chair dining philosophers problem, we used a semaphore with initial value 4, so that at any time there are no more than 4 philosophers who could sit down. So at the very beginning, we see a sequence of SW tag. If you do not remember the meaning of this tag, please go to the Help button and click there. Then you'll see history graph tags. So SW means semaphore wait. So here we see that philosopher 0 wait on a semaphore. And then philosopher 1 does the same, followed by philosopher 2, philosopher 3, and the philosopher 4. Now let's take a click on a tag to see the statement that causes this tag to appear. Of course, these philosophers try to get a chair. Therefore, the first wait is the for chair dot wait, waiting for a chair. Then a philosopher 4 waits for a chair for a while, and then we see the SE tag. The SE tag means semaphore exit. So philosopher 0 waits for a chair, getting into a semaphore. Then when you see the SE tag, it means that thread exits the semaphore. So from here, the SW tag to SE, the SE tag, philosopher 0 is blocked by the semaphore. After SE, philosophers returns to the running state. So for the same reason, philosopher 1 waits for a chair and then release here. Philosopher 1, as a result, has a chair. By the same reason, philosopher 2 has a chair, philosopher 3 has a chair. Now, when philosopher 4 started to wait for a chair, because all 4 chairs are occupied by philosopher 0, 1, 2, and 3. Philosopher 4 cannot get this chair. So this is the beginning of this program. Now, look at the right side. You will see a button showing to you Semaphore. If you click on Semaphore, now you see we have 3 columns. The first column shows to you all semaphores created so far by the program. The second row indicates the counter value, which is 0. Why is it 0? Because all 4 chairs are occupied. When a philosopher gets a chair, the counter would be reduced by 1. As a result, after all 4 chairs are taken, when philosopher 4 tries to get a chair, no chair is available, and the philosopher 4 is waiting. This is the number of waiting threads. Now, if you wish to know a bit more detail, click on the semaphore name line. You will see a small window appears. This window shows to you some information. The first one is, you see, the semaphore name is listed here. And then the semaphore value is here, 0. Because the semaphore count is 0, no one can get in or passing through the wait. Therefore, we have red lines for this signal. Then who are waiting there? All the waiting threads on this semaphore are listed here. So in this case, we see only 1 thread is waiting, philosopher 4. Now, if you compare the results here and the results here, all 4 philosophers 0, 1, 2, and 3 has the chair. They don't need to wait. And only philosopher 4 is waiting on the 4 chair semaphore. Now, you could also see the thread hierarchy here. So now, this from SW to SE indicates waiting on the 4 chair semaphore. Now, let's get a few more steps done. Now, you see something different. Here we have a sequence of SW and a sequence of SE. And the philosopher 4 is still being blocked. And philosopher 4 is waiting here. Now, the next part is MW and ML. The tag MW means it is a mutex wait. Remember, a philosopher, after getting a chair, must pick up his left chopstick, followed by his right one. And each chopstick is protected by a mutex lock. So when you try to execute a mutex lock, you will see this tag here, MW. So here, after getting the chair, philosopher 0 waits for his left chopsticks, and it waits for a while, that is staying in the mutex lock. And then when we see ML, ML means the lock is acquired. So from here to here indicates philosopher 0 is waiting for his left chopsticks. By the same reason, from this MW to this ML, philosopher 1 is waiting for his left. And then, of course, here to here is the time period for philosopher 2 to acquire his left. And by the same reason, philosopher 3 is waiting for his left chopsticks. Now, once we see ML, it means that thread has successfully acquired the indicated lock. Therefore, the process or thread start to run. So at this moment here, all philosophers from 0 to 3 are running. But philosopher 4 is still waiting for his chair. As a result, philosopher 4 is shown in red, blocked. Now, after getting the first chopsticks, philosopher 0 waits for the right one. Philosopher 1 also waits for the right one. So do philosopher 2 and the philosopher 3. As a result, all 5 philosophers are blocked. Let me repeat. From this history window, you see that philosopher 0, philosopher 1, philosopher 2, and the philosopher 3 are waiting for their right chopsticks. Unfortunately, the right chopsticks needed by philosopher 0 is being held by philosopher 1 as its left chopsticks. So if we continue this program, we will immediately notice that philosopher 3 has its left chopsticks and waiting for its right. Now, because philosopher 3's right chopsticks is the left chopsticks of for philosopher 4, but philosopher 4 is blocked because he does not have the chair. Therefore, we can expect that philosopher 3 will very soon get an ML tag and start eating. Now, before we continue, please look at the mutex here. If you click this mutex button, you see all names created, all mutex names created by the threads so far here. And the number of waiting threads are listed here, and the owner of that thread. Remember, when we talk about mutex, each mutex has an ownership information built in. That is the thread that successfully acquired that mutex would be the owner of that mutex. So if you look at it, this one, chopsticks 1 is 0. No one is waiting. Why? Because chopsticks 1 currently has the owner, philosopher 0. But why is there no thread waiting? It's because chopsticks 1, that is the left chopsticks of philosopher 0, is the right chopsticks of Philosopher 4. And the Philosopher 4 now is blocked by the 4-chair semaphore. Therefore, Philosopher 4 will not be able to wait on the Mutex chopsticks 1. The remaining are obvious. Chopstick 2, 3, and 4 are being weighted by Philosopher 2, 3, and 4, respectively. Therefore, between a MW trying to acquire a mutex to a ML tag, which means the lock has been successfully acquired. So looking at this history bars, Philosopher 0, 1, 2, and 3 have their left chopsticks, and they are all currently blocked by the right chopsticks mutex. So let's execute a few more steps. Now, because the right chopsticks for Philosopher 3 is available. Reason is because Philosopher 4 cannot eat. Therefore, Philosopher 4 cannot pick up its left, which is exactly the right one for Philosopher 3. So here, Philosopher 3 gets the semaphore, gets the left chopsticks, get the right one. So Philosopher 3 has a green bar, meaning start eating. Now, Philosopher 3 has a new tag, MU. MU means after eating, Philosopher 3 releases its left chopsticks. Let's take a look at it. And unlock. Okay? Now, if we click on MW, the lock for the right chopsticks. So here, the Philosopher 3 gets a chair, get the first chopsticks, get the second chopsticks, and then finishes eating by unlock. So far, Philosopher 3 releases his left chopsticks. The next step is, of course, releasing its right chopsticks. I hope you understand this so far. Now, because Philosopher 3 finishes eating, it's still in a running state. Therefore, Philosopher 3 is running. Now, Philosopher 2 get a chair, acquired its left chopsticks, and acquired its right chopsticks. Therefore, Philosopher 2 is running. So this is the basic interpretation of SW, SE, MW, ML, and the MU tags. But we actually could see more, because from here, you have to find out why Philosopher 2 could get his right chopsticks. This is his left one, this is the right one. Of course, if you know the program, you know Philosopher 2 could get his right chopsticks because Philosopher 3 releases his left chopsticks. But this relationship is not so obvious by simply looking at this history graph. So what we need to do is click the semaphore button. If you don't use the semaphore, it's okay. And if you use the semaphore, strongly encourage you to click on the semaphore button. Because this program also uses Mutex lock, so we click on the Mutex lock button. Now, instantly you see a short segment joining the MU and ML tag. This short segment, let me call it link, indicates the relationship between this MU and this ML. In other words, Philosopher 3 releases left chopsticks for Philosopher 2 to pick up. Now let's run for a few more steps. It's even more interesting. Now, Philosopher 3 releases his second chopsticks, but no one picked it up because that is the right chopsticks of Philosopher 3. And the Philosopher 4 at this moment is still waiting for a chair. Now you see a new tag, SS. The tag SS means Semaphore signal. Now get back to here. Wait for the left chopsticks. Got it. Wait for the second chopsticks. Got it. Release the first one, which is picked up by Philosopher 2. Release the second one. No one gets it because Philosopher 4 is waiting. And then finally, Philosopher 3 finishes eating. Then Philosopher 3 must release the chair. Let's click on SS. Now, as you can see, Philosopher 3 executes the signal to the 4 chair semaphore. Now, because Philosopher 3 exits, so of those 4 chairs, we have one more available. Take a look at the semaphore. Do you see that? Okay. After this signal, the value of the chair counter returns to 3. Now, Philosopher 4 got it because Philosopher 4 is still waiting when this signal happens. Once the signaling operation completes, Philosopher 4 is able to get the chair. So Philosopher 3, after finishing eating, he comes back for the next round, waiting for the chair again. But this chair, released by himself, was occupied by Philosopher 4. Therefore, we have a waiting thread. And who is waiting there? As mentioned earlier, is Philosopher 3. Click on this, isn't it? Philosopher 3 is waiting. Now let's get back to the mutex. And we see Philosopher 0 is waiting, Philosopher 1 is waiting. So let's click on chopsticks 2. So a mutex window appears. And this window shows that it is mutex. The name of that mutex is chopsticks 2. And who is waiting? Philosopher 0. And the lock is locked. The owner is Philosopher 1. So let's quickly go through these steps. SW, semaphore wait. SE, semaphore exit. That is, the thread passes the wait. And SS here, semaphore signal. Now for mutexes, MW is mutex wait. ML means mutex lock, meaning the thread becomes the owner of that mutex. MU means we have finished using the mutex, we execute and unlock. So right after you unlock a mutex, someone may pick it up. The one who picks it up would have a link between the unlock and the lock. Similarly, when you execute a semaphore signal, releasing the semaphore, and if there are some waiting thread there, one of them would get that signal. As a result, that thread continues. So there will be a short link between the signaler and the released threads. Let's go through a few more steps. Now, Philosopher 2 um, got the first chopstick, the second chopsticks. After finished eating, Philosopher 2 releases left chopsticks. His left is the right of for Philosopher 1. Therefore, when Philosopher 2 releases the left, Philosopher 1 later on could pick it up. Now, Philosopher 3 releases right chopsticks. Now, Philosopher 4 has its first one because Philosopher 4 got the chair released by Philosopher 3 and waits for its left. And this left is exactly the right of Philosopher 3. Now, after eating, Philosopher 2 signals releasing the chair and taken by Philosopher 3. So from this history graph and these short links, remember, in order to get these short links, you have to click on the semaphores button, and the mutex button lists on top of the history graph. To verify the detail of each semaphore and each mutex, click on the mutex button to see the mutex name, how many threads are waiting, and the owner of that particular mutex. And click on the semaphore button. The display area shows the semaphore or semaphore names along with their values and how many waitings. And if you want to see the detail, click on semaphore. You will see the corresponding semaphore name appear. Do the same for the mutex. In this way, using the animation by making it faster, slower, or resume, pause, and so on. In particular, I personally prefer to step it through. Always remember, stepping through simply goes from one thread management or synchronization activity to the next one. It's not a stepping through statement by statement, nor instruction by instruction. In this way, the activity that happened in your ThreadMentor program using Semaphore and the mutex lock could clearly be reconstructed. You could use this reconstruction for your debugging purpose or to verify whether your logic is correct. As a result, the history graph plus the thread hierarchy windows, and of course, the mutex windows and the semaphore window would help you significantly in writing and designing a program for program assignment 4. Now, before we end this demo, I'd like to tell you two important things. Remember, when we talk about the creation of threads and the writing the statement for a thread in a thread func, to execute a created thread, you call the begin method. Now, at the end, in all of my program, example program, we always have a call to the exit method, where E in exit is the uppercase, in order to differentiate from the system call or lowercase exit. Why you should always at the exit call as your last statement or the last executable statement in a thread. That is because you have to inform the visualization system so that the visualization would know a particular thread has completed its execution. And the visualization system will not expect anything from that terminated thread. So always at a call to the exit method in your program. The second one, the second node is probably more important, but you may not notice this issue. As we mentioned in our previous demo, when we talk about quicksort, we indicated that your program using visualization is compiled and run. And your program does not have to do anything with respect to visualization. You just compiled it with ThreadMentor visualization library. Everything your program will be doing with respect to thread activity or thread management activities and the thread synchronization activities are all hidden from you. The visualization system is run in a separate and independent address space. So how does visualization knows what has happened in your program? It's very simple. The communication between your program hidden from you and the visualization system is done by the use of message queues. That is, when a thread management activity or a synchronization primitive is encountered, something behind you, which is implemented in the thread library as well as in the Mutex and the Semaphore class. A message will be sent to the visualization. For an example, suppose Philosopher 4 execute SE, that is exit the semaphore wait. Hidden from you would be a message which include the thread and thread name and what kind of synchronization primitive it is, in this case, semaphore, as well as the counter and the waiting list of that semaphore. This whole bunch of information will be sent to the visualization automatically. On the other hand, the visualization system would receive this kind of a message from your program. For the visualization to construct a tag, even include the line on which that particular signal was executed. And the ownership counter, waiting list, and so on would be used to display this panel and the details of each semaphore and each mutex. Therefore, whenever you do a thread management operation or a thread synchronization primitive, whole lot of information will float from your program to the visualization system. So what is the problem anyway? The problem is not you nor the visualization system. It's the operating system. Now, message queue is a mechanism built into an operating system. So when you want to use this capability, you need to have a system call. So when your program execute SE, this information will be sent to the operating system through a message queue from your program to the visualization system. On the other hand, the visualization system itself is rather simple. Whenever it sees the message queue has a message, it just pick up that message and use the contents provided in the message to construct all the needed windows and to display all the needed information. So in this way, even though it looks easy from your program point of view and the visualization, actually it's a big loop. You send the information through a message queue with a system call. The operating system gets an interrupt, which is a trap. Remember, a trap is an interrupt generated by software. Then operating system would have a interrupt handler to analyze what's going on. That interrupt handler finds out who should be called in order to process this interrupt. Then the operating system would put the information into the place where the visualization system could get it. So this is a long way to go. Furthermore, after the visualization system receives your message and successfully put all the visual elements into every possible window, your program, of course, hidden from you, will receive an acknowledgement saying that what you asked the system, the visualization system to display has been completed. So it's a long cycle. Any time when you get into the operating system, it's going to be time consuming. And it's even more important. You have so many threads running concurrently. Every thread is capable of doing some thread management capability or synchronization primitives. So all of your threads could send message to the visualization system. For the visualization system, the queue that contains this message could be rather long. The visualization system simply gets one message, displays it. After doing it, tells the sender that, okay, you're done, then process the next one. Therefore, the visualization system would take a longer time to get the display done. Probably more time consuming than simply running your program without visualization. Therefore, this is the consequence. in your program, you may have some output. The output would just be so simple. Your output is sent to the STD buffer so that it could be displayed on your terminal. Very simple. But when you want to do visualization, as we mentioned, it's going to be a large number of steps to be followed. Therefore, there could be a delay in your visuals. In other words, you may have a feeling occasionally that your program runs faster than the visualization. And sometimes the display of each window, in particular Semaphore and the Mutex windows, your program has already shown that a thread has passed a signal or get into the critical section. But the Semaphore or Mutex window may still be showing that that thread is still waiting. Similarly, in your program, or in particular in the history graph, it shows that a thread has already exited a mutex. But if you look at a mutex window, that thread may still be inside the critical section, holding the lock. So in this case, don't worry, just allow it to run for a few more steps. And the use of step button is more useful than the use of animation. So I hope you understand these two issues. This is the end of part 5 of Semaphore discussion. The next unit should be available later this week. We'll revisit race condition, telling you something in debugging. Catching race condition is a very, very hard problem based on the Turing machine's model. More accurately, catching race condition in a program that uses multiple semaphores is an NP hard problem. Very difficult problem to solve, and there may not be any solution at all. Therefore, when you use semaphores in debugging, you have to be very careful. So in the next unit, I will show you several examples showing you some common places where race condition could happen.